Um, Hi, I'm Shimokrachuri. Welcome back to the Thursday colloquium at IUCAA, which we have been doing from early April, and pretty much every week we have had a couple of gaps. I'm very happy today to welcome an old friend of ours, Volker Springel, to give the colloquium today. Volker needs no introduction to this audience, but let me say that he's a director at the Max Planck Institute in Garching. And of course, he did his PhD in Munich and then spent some time at the CFA as a postdoc and has been since then associated mostly with the Max Planck Institutes at Garching and Heidelberg, because he's been a professor at Heidelberg University as well. But we know Volker for his pioneering cosmological simulations, and of course, with the Millennium simulation becoming one of the basic things that almost everybody in cosmology used for a long time. And of course, he's moved on to much bigger simulations, which he'll talk about, I'm sure, today in a perspective, give us a perspective of hydrodynamical simulations of galaxy formation and cosmology. Over to you, Volker.
Yeah, thanks a lot for this nice introduction, and thanks a lot for your interest. I really appreciate it that you invite me during these times, and I'm glad to be here with you today, at least in cyberspace. So I would like to give you a little bit of an overview of my research work in studying galaxy formation in the universe with the help of big computer simulations. So I'd like to introduce a little bit the methodology to you there and highlight some of the problems that have been partially solved and that are still bothering us today, and give you basically a flavor of the state of affairs in this type of work. So let's see. Let me maybe just for a start remind you, of course, that the basis of this is very much the enormous progress we've witnessed in cosmology, and you're aware of this, obviously, that with missions like Planck, we have constrained the microwave background to a stunning precision, and this, together with a whole slew of other cosmological observations, has tied down our standard model of cosmology with is lambda CDM. A minimal 6-parameter fit describes most of the cosmological data we have, and you know that this standard model is well constrained. It features two puzzling things: the cold dark matter component and the dark energy component, described with a cosmological constant in the standard model. Both of these components are, of course, fundamental physical puzzles, and much of the current work in cosmology is actually geared towards finding cracks in this model. I will not talk much about this. I rather take these initial conditions, in a sense, that are laid down by the cosmological standard model accurately and unambiguously, namely in lambda CDM. And I'm studying the problem how out of this very simple state left behind by the Big Bang that we see in the microwave background, how we come to the complex galaxies we see today. Because principally, if you know the initial conditions, then studying the evolution of the universe is an initial value problem. It's governed by physical laws we basically know, and if we integrate the differential equations forward in time, we should be able to predict everything out of this initial state. And this is very much the concept of much of computational cosmology. We try to predict what these initial conditions give rise to, whether they really make big spiral galaxies like our Milky Way. And these are, of course, extremely complex objects in their own right. And it's the question whether this strange composition of the universe we assume exists, namely cold dark matter and dark energy and a tiny mixture of baryons, actually gives rise to these galaxies. And just to flesh this out a bit more, the equations, of course, that need to be studied here are complicated. I just want to flesh some of these systems. For the hydrodynamics, this is the hyperbolic system of conservation laws. described by the Navier-Stokes equations, which you see on the right. These are just conservation laws for mass, momentum, and energy. They are nonlinear partial differential equations and relatively complex to solve directly. Actually, this is very, very hard to do. And as you, for example, processes like turbulence are still not very understood even today. Right? So these equations, hydrodynamics, are already difficult, but we are not done, right? We need the dark matter. Dark matter in the standard scenario is a collisionless fluid described by a seemingly simple equation, the collisionless Boltzmann equation, which I'll show you down on the right, coupled to the Poisson equation, which describes self-gravity. And this system of partial differential equations is actually an integral partial differential equation, and it's 6-dimensional in the phase space and plus the time dimension. Very hard to solve, except for in trivial situations, for example, say spherical symmetry or so. That's why there are very few analytic solutions known for these systems, especially also if you couple them as is really needed in the universe. Plus, there are further complicated equations, radiative transfer, for example, magnetohydrodynamics, aspects of general relativity, which is a particularly hard system of partial differential equations, highly nonlinear. You know that. And it's clear that analytic pencil and paper solutions are insightful, but can only be reached in limited number of cases. And that's why we basically try to do brute force solutions of these equations. We try to solve them nevertheless, but in an approximate discretized way by turning to supercomputers. And those, of course, have made huge strides forward in time. We have much higher computation power nowadays than we used to, and this keeps growing in large parallel machines. And the idea then is to apply these machines to solve the dynamics of the universe. If you do this in the lambda CDM cosmology, for a long time we've done this by considering simplified models of the universe. You basically take the mix of matter and dark energy that you have, shown here on the left. This is the composition we have from the Planck cosmology. And if you replace the ordinary baryonic component and make this also dark matter, you arrive at dark matter only universes. Those are much more simple because you don't have to deal with the baryonic equations, with the hydrodynamics, only with the collisionless dark matter. And that gives rise to the dark matter only simulations. One was mentioned in the beginning, a work that we've done here in Garching 15 years ago now, the Millennium simulation, produced a first nice, also visually stunning picture of the cosmic web that's arising as kind of a non-linearly sharpened version of these initial conditions we see in the CMB. And this is now common knowledge. Of course, we have this cosmic web, as this is called, composed of filaments, and in the intersections of these filaments, you have big nodes in the cosmic web. The biggest of these are large galaxy clusters, like you have here in the center. And this is the dark matter backbone on which the galaxies are growing, and we think they decorate these nodes along this cosmic web. And so what has been done over the past, say, 2 decades or so is to invest a lot of work in really understanding precisely how these adiabatic Gaussian initial conditions seen in the CMB, how they transform to nonlinear structures in the today's evolved universe. Here in the dark matter component, and if you zoom in these dark matter lumps, you see that they have a rich phase-space structure. There's a dark matter halo here on the lower right is actually predicted to be very lumpy, containing a myriad of tiny little lumps, other structures that have fallen into the big halo during the hierarchical growth. And then you get this very complex phase space in the dark matter halos. And nowadays, these studies are very mature. We can use these dark matter simulations to predict, for example, basic things like the abundance of halos as a function of mass and epoch, very accurately, their spatial distribution, the clustering properties, internal properties like concentration and so on. And that's all very important because 85% of the mass are in the dark matter in the standard model. So if you understand this component, you already learned a lot. And in fact, I would argue that the dark matter growth in the standard cosmology is really rather well understood. These methods are quite mature and we know these things. And on large scales, these models actually predict a clustering of halos and of galaxies, very much like the one we see in real galaxies. This is shown in this diagram from the Millennium simulation, comparing in blue here various redshift surveys of galaxies, and in red are mock catalogs constructed from this Millennium simulation. And these mock galaxy surveys, they basically look statistically pretty much like the observations. There is generally relatively good agreement on large scales. So that's encouraging. And you can push these dark matter simulations further. In fact, today we have a paper in, just by accidents in the journal Nature discussing maybe the most advanced dark matter only simulation so far. That's one that zooms in all the way from the biggest structures in a large piece of the universe, 100 megaparsec apart, down to the smallest dark matter halos we expect. In typical WIMP scenarios for the dark matter, where you have a certain finite thermal velocities nevertheless, and then limits the smallest halos you'll get. They will be typically of Earth mass. And these Earth mass dark matter halos you see are actually in the lower right. And that's a zoom over about 30 orders of magnitude in mass. And it gives an illustration how adaptive also these simulations have become. So meaning we can really study the dark matter halos from the tiniest ones that exist to the biggest ones that exist. So this problem is certainly not solved completely, but is rather mature. So we can do that very well. But what we can't do very well is to do the hydrodynamical problem. That's sort of the main topic of my talk. What if you don't make this simplification? If you actually study the ordinary baryons too, then the problem is becoming the real problem, and it's becoming a incredibly far harder problem, because of course in the ordinary baryonic matter, there the luminous components of galaxies form, the stars. You will also have to deal maybe with supermassive black holes, with stellar evolution, with plasma physics, with magnetic fields, and all the mess there is. And that's something that I would like to discuss now a bit. So from early on, people tried to not only do dark matter simulations, but do hydrodynamical simulations of galaxy formation in the full cosmological model. But the problem was that this actually was fairly unsuccessful for a while. In particular, with respect to the problem of making disk galaxies, like the Milky Way, say, this has proven to be very hard and largely unsuccessful for a long time. Here, I show you a result from 2003, which was at the time a breakthrough in the sense that these work by Abadi et al. Formed for the first time in a cosmological setting, a disk galaxy, which you see basically here on the right. The star particles are shown here from high redshift to low redshift, and on the lower right you see a bluish disk galaxy on top of a reddish spheroid. Now, the authors here have plotted this in a clever way, because they plotted the disk particles on top after the spheroid particles, because they are actually a subdominant in mass, which you also can appreciate from the rotation curve decomposition here on the left. This is the rotation curve of this disk galaxy, and it shows you in the center a rotation of 400 to 500 kilometers a second, then rapid fall to about 200 kilometers a second, quite unlike anything like the Milky Way, even though this is an object of total Milky mass, about the Milky Way mass of 10 to the 12. And so it should actually slowly climb up or rapidly climb up to 200 and then stay flat. And the reason why this is so strange in shape is because there was a huge spheroid of stars at the center, a big bulge. And that formed, and in general, the galaxy was way too massive. It contains too many stars. This has become known as the so-called overcooling catastrophe, the tendency that even in a low resolution simulation, you find that the cosmic gases will cool very efficiently and collapse then under the weight into the centers of dark matter halos and make a lot of stars there, far more than you see in the real universe. And this is another early result that illustrates this. This is a cosmological simulation that shows the cosmic star formation rate history here on the left, with some data about 15 years ago, the state of affairs then. And you see that this low resolution cosmological simulation predicts a cosmic star formation rate density, so the star formation rate per unit volume as a function of time, which is a factor of several above the observations. If you integrate this over time, you'll then predict the total density in stars in the universe will be a factor of several, too large at least. And if you make the simulation better by using higher resolution, it will actually climb up further. So this is the overcooling catastrophe. And on the right is a comparison between the observed luminosity function, which are the symbols, with predictions from early hydrodynamical simulations. This was actually done here in the GIMIC project, which was a resimulation of regions in the Millennium simulation with hydrodynamics. And you see that the shape we got at the time for the luminosity function is very, very different from what's observed. First of all, on the faint end, you have an excess of galaxies, which is very strong, not this flat slope. At the bright end, which is on the right, you predict galaxies in this simulation which don't exist in nature. They are far too massive. And the exponential decline in the abundance, the so-called Schechter function decline at the knee, is also not seen at all. And here where the Milky Way should sit, you have this strange feature, a dip. So, you know, it could hardly be worse compared to the observations. So this is a big, big failure. But the situation has improved, especially over the last 10 years. And starting with this work, for example, Scaglia-Pieco, 2011, they looked at Milky Way-sized galaxies again and got now a disk, sort of a disk. You still clearly see a relatively big bulge and bar in the center. And then quickly, other groups found ever, in steps, ever better simulations. You see here some works from 2011. Then a couple of years later, you see that the disks start to look more disk-like, right? So if you look at this edge-on result here from Mainacci 2014, you see an edge-on disk which doesn't have a big bulge at the center, at least not very strongly anymore. Similarly, Phil Hopkins here in the same year. And here on the right, you see that there are dust lanes suddenly showing up. So they also visually, these simulation outcomes, they look more and more like galaxies. And this is a current one from last year. Here, a disk galaxy seen phase on, but that's not actually an observation from the Hubble Space Telescope or so. You maybe from a distance you might mistake it for a real observation. This is a hydrodynamical cosmological simulation, and you see a bluish region which are star forming and dust lanes on top. And here's the thing rendered from the side. Of course, making the images is also important. These are here produced by detailed radiative transfer simulations to make them look realistic. If you do that, however, you do get nowadays relatively realistic images that look like real galaxies. So what happened here? Why was, what's the basis for these better predictions? And well, the main reason is clearly that people managed to curtail the overprotection of stars by alluding to so-called feedback processes. And feedback here is a summary term that means that you allude to physics that slows down star formation one way or another. It slows it down by considering that stars return energy back into the interstellar medium, for example, through supernova explosions, by their light, by their hard UV radiation, maybe heating the surrounding gas that way, by the radiation pressure that's exerted by the light of young and massive stars. Maybe you have also other types of effects, like in particular AGN supermassive black holes at the centers of galaxies, releasing during certain phases huge amounts of energy, and may be able to kick out galaxy gas in very large galaxies. You have, in some simulations, considerations of non-thermal particle populations, so-called cosmic rays, supporting the gas, and so on. So this is just a shopping list on this slide, a bulleted list of, in detail, rather complicated physics that has been often in grossly simplified ways included in the simulation. And with that, the star formation rate was slowed down. And that's fundamentally the main reason why the simulations got a lot better. And then they agree, after tuning some of the efficiencies of these processes with the observed stellar masses. The other reason why the simulations nowadays are so much better is because there has also been a fair amount of progress in the numerical methods themselves. So some of them are just faster, of course, but also more accurate than other methods. Here I show an example of this. Here on the right in these images, you see this galaxy. This is actually the gas component, the temperature, and the gas density. It's a simulation here on top and on the bottom that use the same initial conditions. It's a cosmological simulation, and here we see a zoom at the center of one of the dark matter halos. And in the gas, you see basically a rotationally supported cold gas disk here. It has some spiral arms and so on. And on the bottom, the same system at the same resolution is simulated with the gadget code. It's an older SPH code that I wrote at some point. And this up there is our more modern moving mesh code, a repo, which does the hydrodynamics better. And you basically see that these calculations are not identical, even though the physics is exactly the same. The only difference is the numerical method, the numerical discretization method. And the bottom one is basically much more noisy, and that affects the smoothness of the flow that you get, affects the accuracy of the result. And in this case, makes the disk galaxies that you get to be much smaller and look more ratty than they should really be. And, you know, among the pundits in the field, there are then big fights about, you know, which code is better in which circumstances. I think this is important to ultimately do, because these code inaccuracies, they can impact the results. So one has to work on these technical aspects and basically do the best job one can do. But it's also clear that you will always have numerical inaccuracies, and one has to be, you know, aware of that and be trying to make these errors as small as possible, but not trying to put them under the rug. I think is also important. So here is a little video of our moving mesh code, a repo. I'm not sure whether you can see this very well via Zoom. I hope you get at least a few frames occasionally. And basically what you see is a Voronoi mesh that's dynamic. It is created by a set of mesh generating points. So every cell here is defined as the region that's closest to one of the mesh generating points, closer to any of these other points. And in a second, you maybe see in this visualization some of these points. And what then the hydrodynamical method is doing is that it's computing so-called fluxes over the edges, over the interfaces of these cells. And that's done with so-called Riemann solvers. And the advantage of that is that you have a relatively accurate discretization of the fluid equations with which techniques that are mature and well established and tested for a long time on Cartesian grids mostly. But here you can now apply this to an unstructured mesh that is adjusting to the geometry that we need. And because the mesh with this technique can flow along with the gas, you can handle in particular very supersonic motions very well. And that's very common in the area of galaxy formation. So we think we have with this code a particularly good method that is well adjusted to the problem of galaxy formation. And now I will discuss a bit what one can do with it and what the state of the art is in these cosmological hydro simulations. In fact, over the last couple of years, several groups have published very large, very expensive cosmological hydrodynamical simulations. For example, Illustris was our own work, first work in this attempt, 2014. Our Horizon AGN, Magneticum, also in the same year, an Eagle just a few months later, a massive Planck too, and then later our current flagship project, IllustrisTNG. So you see, this is a kind of an active field, and all of these simulations, they have made really quite substantial progress in predicting the whole galaxy population directly in these hydrodynamical simulations. So, for example, in Illustris, our biggest success with this was maybe that we got, for the first time, the morphological mix of galaxies roughly correct. So these are stamps excised from different dark matter halos out of this calculation, and you see basically some stars are making up elliptical galaxies, some systems are disk galaxies, and they have spiral arms, and some have bars. Then you have some train wrecks down there, irregular galaxies. And these images here have been arranged, in resemblance to the tuning fork for a diagram of Hubble. And you can, in fact, do morphological classification with the Hubble sequence here, and you do get plausible morphologies for the galaxies. And importantly, they also vary systematically with stellar mass, just like it's observed that bigger galaxies come preferentially as ellipticals and lower mass ones preferentially as disk systems. And this is something that is not tuned in any way. This arises naturally in hierarchical galaxy formation within lambda CDM, and that's a reassuring finding. And the basic physics that's entering these simulations are more or less the same, and also in the other group's calculations. You model gas cooling in the diffuse gas. So this is comparatively well understood how after being shock heated in halos, how the gas then loses energy via atomic line cooling and Bremsstrahlung emission and so on, settles into rotationally supported disks. Once it's cold in disks, you then have a prescription for, because you don't have the resolution to see individual stars, of course, neither that, the ignition of nuclear burning is obviously unresolved. So you have to model this in a subgrid way by typically replacing very dense pockets of gas with some prescription with a stellar population. That's the so-called star formation modeling that needs to be done here on the cosmological scales. Associated with this then is also some modeling of the feedback associated with stars, with stellar evolution. So massive stars will burn out, explode, so they return metals and energy back into the star-forming gas. This has to be modeled, and there are many different approaches for this. But we have, for example, an explicit ISM model, which is very simplistic, but has the advantage that it's a clear closure for the hydrodynamics on unresolved scales, plus a by hand wind model that tries to take care of the mass loss that is required in low mass galaxies. And thirdly, there are black holes. This is sort of a more recent and more complicated addition, but more and more I think the community agrees that the quenching, so-called quenching of galaxies at the massive end, namely the fact that the largest galaxies appear to be stopping forming stars fairly reliably and fairly rapidly, this quenching process cannot be understood with stellar feedback alone. It can be relatively easily understood with supermassive black holes and their associated energy liberation. And so black hole feedback is invoked commonly now at the massive end, and that needs to be then included in these simulations too. Of course, this is an extreme dynamic range problem too, to follow the accretion of gas down to the last stable orbit into a black hole. And this cannot be done in general everywhere in a large cosmological volume in a simulation. So here too, one needs very simplified models. And later I get to some results in the IllustrisTNG. So these models, they added magnetic fields, for example, and they also greatly changed, in particular, the treatment of black hole feedback to inline the results much better with the observations. So talking about IllustrisTNG now, this was produced by this team of people. We had worked for a couple of years quite intensely together to make these calculations possible, and very grateful to this to my collaborators. Lars Hönkes, of course, as co-PI, and then Annalisa Pilipic, Rüdiger Packmore, Dylan Nelson, Rainer Weinberger, Federico Mainacci, Mark Vogelsberger, Shai Gehner, Jill Nyman, and Paul Torres. So these was really a very nice experience, because I think we really produced a quite stunning result, namely this set of calculations. IllustrisTNG, these are now, I think, state-of-the-art cosmological hydrodynamical simulations done in 3 different volumes. We have done 3 calculations in different box sizes from 50 megaparsec, 100 to 300. The reason is simply that with this technique, you can cover a wider dynamic range in scales. This big box is very useful to study rarer objects, rich galaxy clusters, for example, and also clustering of galaxies on the larger scales. For this, you need to have a decent volume. You know that the baryonic acoustic oscillations, they come on scales of, say, 120 or so megaparsec. They are kind of not barely contained in this big box, and they are not even contained in these smaller simulations. But these smaller boxes, they have then better mass resolution, and you can use them to focus on the smaller objects like dwarf galaxies, for example. And we made some of these simulations publicly available. This has been actually huge success, because in that way, many more people can use this theoretical data to do analysis of and pursue ideas that we haven't even had ever. And so we are very proud that already 170 papers have been written with this data, because we made it publicly available. And if you're interested in this, plus check out our website. Just to comment on the computational costs, so these simulations were fairly expensive. The biggest one, TNG 50, used more than 100 million CPU hours on this machine, which is already unfortunately dismantled. It was a Cray, very nice Cray machine, Hazelhen here in Germany, the computing center in Stuttgart. And when you are in this business of running a supercomputer center, you have to basically throw out your machine every 3 to 5 years, even though they're extremely expensive, replace it with a new one, because otherwise you basically can't compete with this race to build ever bigger machines. But we are benefiting from this very much in cosmology, from this race. And here I show you a time evolution now. Again, this is a video that you may or may not see reasonably smoothly. If you see it in HD quality, as I have it here on my monitor, it's really quite nice. So I encourage you to check out the IllustrisTNG website for many movies of the simulation, this one and many other ones, where you can take a look at, how cosmic structure formation works and how galaxies come together in a high resolution hydrodynamical simulation. Here you see redshift 2.1. It's a zoom in on a small region from TNG 50. And you see how this galaxy forms. These are the gases that stream together. You see that the gas flow is kind of quite messy. There are some preferred directions, filaments that feed this disk system here, which is at the moment stopped, and it's rotation supported. Here you see on the left the metals that have been created by the stars and are ejected by some of the winds. And in this halo, you have fairly turbulent flow. In fact, the level of turbulence that is expected is huge. The Reynolds numbers of these flows are far higher than anything we have on Earth. So it's extremely challenging to do justice to the turbulent cascades that you expect in such galaxies. But now, below redshift 1, the disks have formed very well, and you see that they are in place now. They keep forming stars at a relatively constant rate, and then make big disk galaxies that way to the end. And sometimes you have a little guy coming in here, a little merger. Of course, these simulations also predict satellite galaxies and how many mergers you have, whether disks can survive that, etc. And with TNG, we for the first time were able to produce the bimodal color distribution of galaxies that's seen in surveys like the Sloan Digital Sky Survey rather well. This is shown basically in these histograms. Here are different mass bins and the SDSS observations, which are fairly precise, are shown as the black histogram, and the blue one, that's the IllustrisTNG. And you basically see here that the blue sequence, which are the star-forming galaxies, and the red segment, they appear correctly as a function of stellar mass and roughly at the right size. And that hasn't been possible earlier in earlier calculations. And that's one basic with success, because it shows that the quenching of the massive galaxies worked reasonably well. And another way to check this is to look at galaxy clustering. Here's again a comparison of the two-point correlation function of galaxies in different mass bins. In the low edge of the universe, the Sloan Digital Sky Survey results, which are extremely accurate, are these black points. And in red, you see the prediction from the TNG 300 calculation. Bluish is our smaller box, TNG 100, which is high resolution. And you see that, especially at this intermediate masses, the match between the hydro simulations and the data is actually pretty good. So it's certainly encouraging. And especially if you also look separately at blue and red galaxies, you see that they are also reproducing the observed clustering difference in these different populations quite well. So that was extremely encouraging initial result. But it is, to me, actually quite stunning how many different properties are simultaneously reproduced by this calculation. Often not exactly, but in good approximate ways. For example, here the galaxy sizes of late type and early type galaxies match data reasonably well. Or here is a comparison between the Pan-STAR survey and IllustrisTNG in a multidimensional plot that looks at the galaxy morphologies as a function of stellar mass and concentration. And basically, there are something like the Gini coefficient, a measure of concentration, and the bulge statistic is a measure of the morphology of the galaxies. And if you look at these colored maps, the color here is the concentration. You see that the locus of the galaxies predicted in IllustrisTNG and the Pan-STAR survey is actually fairly similar. And this is also, if you look at this more quantitatively, the mean trends with stellar mass are actually reproduced quite well. On the other hand, not everything is correct here. If you look at final things, so I would basically summarize this as saying, so to first order, the morphology stellar mass trends are matched well, but there are certain second order effects that are not reproduced. For example, in Pan-STARs, there is at a given stellar mass, there's still a correlation between morphology and color. This is basic because here, for example, 10 to 11, that the red points are clustering on the top via these green points. And in IllustrisTNG, you don't have this. There is no strong morphology color correlation. And that's a failure of the model, which means something. We just don't know for sure what it means, but we believe it has to do with the model for black hole triggering activity that is relatively coarse in IllustrisTNG. And potentially, if one makes this better, then this could be explained. And for example, a student of mine has looked at a model that accounts for the black hole spin, and with that he was able to introduce such a correlation into the results. Other tensions exist, which are often discussed these days, between the amount of dark matter that's predicted in the inner regions of galaxies. There is work by Reinhard Genzel, for example, showing that observationally some of the high redshift 2 galaxies have somewhat less dark matter than maybe naively expected in lambda CDM. And here is a comparison between predictions for the Milky Way galaxy that we would make for the rotation curve decomposition. So this is the total one that matches the Milky Way very well. But if you look at the relative contributions to this mass distribution coming from stars and dark matter, and compare basically the simulation predictions we make to the inferences that observers have for the structure of the galaxy, like here Joe Bovee, for example, you see that they predict a much more maximum disk-like model where the stars make a far higher contribution in the inner regions than we would expect based on our cosmological models. So, and other contexts in which this is discussed often is so-called cusp core problem, whether dwarf galaxies, for example, there are dark matter cores or not. And we don't really find dark matter cores, at least not big ones, in our simulation. So that is certainly a room for further work. These cosmological simulations have nowadays also become important to in cosmology because, as I mentioned earlier, modern surveys that target especially dark energy, try to constrain expansion history of the universe, they do this by looking at precision clustering statistics of the matter, for example, weak lensing or BAO statistics. And the modern surveys, they are so good that you need theoretical models that are able to predict the power spectrum of the matter to, for example, about 1% precision. Typically, that's the nominal number that's often mentioned. And here is a comparison of the power spectrum of the total matter field in a full physics simulation relative to the power spectrum in a dark matter only simulation. And you see here that in this dark gray line here, that's the 1% region. And basically you see that on very large scales, the full physics calculations agree with dark matter models. So that's good news because we understand the dark matter models. But then at a certain scale, the baryonic physics modifies the power spectrum by up to 20%. And our older Illustra simulation even had a much bigger impact because of the AGN feedback that was very strong there. So if you aim for 1% precision and you have systematic impact of baryonic physics, 20%, then you are in trouble. So either you have to understand this very accurately somehow from first principles, or you maybe have to exclude it or marginalize over it. So that's something where these hydrodynamical simulations are very important to inform cosmological analysis and also inform us about maybe the impact baryonic physics could have on our inferences. So let me, on this point, say a little bit more about the dark matter, the black hole feedback that's responsible for the most part on this very strong effects on large scales. So, and here I want to sort of lean back a bit and discuss this from a more general point of view and highlight the role of simulations in general in this in our current scientific method in astronomy, because traditionally you have astronomical observations leading to, with some data analysis, to some theory, and the theory creates hypotheses that are then tested by additional observations. And numerical techniques, they are now partnering here in both parts of this classical cycle of work, because we can do numerical experiments to augment the observations. For example, we can throw two black holes together and see what happens, or make a galaxy merge on the computer. And the theory, of course, is strongly empowered by being able to do computer simulations, for example, to actually solve systems of equations that are otherwise intractable. That's why I think computers, as you all will agree with, are helping us basically everywhere, and they have become, I think, part of the scientific method in both ends of this cycle. Now, black holes is one of the most fascinating aspects, I think, of galaxy evolution, because the modern idea is now that despite their tiny size at the centers of galaxies, that they still can affect the whole galaxy all at once. And energetically, this is not implausible, because a quasar shines maybe for 10 to 7 years or so, emits as much energy as a 1,000 billion stars, 10 to the 12 solar luminosities, and that is a total energy about 10 to the 60 to 10 to the 61 ergs, right? So this is basically a billion supernovae, which have nominally 10 to the 51 ergs over one of these cycles. And we also know from observations that in every galaxy, there's about a supermassive black hole. Its mass is about 1,000th of the stellar mass. And so you have a ratio here of the mean black hole mass density and the stellar mass density. And from this energy return that you expect during the growth of the black hole, about 10% of the accreted rest mass energy is liberated. You see straight away that, and you get about 1 supernova per every 100 solar mass in stars, that the ratio of energies you expect from black hole accretion and on all the supernova combined is about the same. So energetically, the supermassive black holes are an important player. What's not clear is when this player is doing its job and how this is actually working in physically. So back in 2005, Tiziana Di Matteo, Lars Höngst, and myself, we did some early papers on trying to model black hole feedback and galaxy mergers at the time. So here you see a time evolution on the right, and we basically put in 2 supermassive black hole models that were allowed to grow via bond accretion at the centers of these galaxies. And when they merged, then there would be a phase where they exponentially start growing, and then the energy output grows exponentially. You have a quasar, and the quasar will stop growing at some point. Exponential growth can't stop forever. And the idea for quasar feedback is that the energy output, the quasar itself, is self-regulating at some level. At some point, it becomes so large that it kicks out its own fuel. And that is the idea of quasar feedback. And this is a process that is still not very well understood. We have much more observational evidence nowadays that this occurs in some systems. On the other hand, the evidence is not so strong that one can argue it's always occurring. So unlike for another type of feedback from black holes, so-called radio mode feedback, that's seen in big halos at the centers, where we often see X-ray cavities and jets. And here the evidence that supermassive black holes do something to centers of galaxy clusters, that's it's infutable basically. It's still unclear how this energy manages to couple in a space-filling way to the gas, whether ordinary jet injection can do that, even though more recent simulations more and more seem to suggest this is possible, that by occasional firing a jet into this cluster at the center from the black hole, you then get all sorts of heating processes, sound waves, ripples, and mixing that can arrest the cooling flow in the cluster and make this a quenched galaxy at the center. And in Illustris, we've tried to model this. I show here a little video. Let me fast forward this. I can. It doesn't work. Yeah, never mind.
Okay, let it run.
Yeah, here you see it. I'm not sure whether you can see it now, but there are explosions emanating from the biggest halos, and these are driven by quasars here that are shining, and that is an extreme form of black hole feedback. You get these storms here. This is the fluctuating radiation field from the quasar, changing ionization state, and then strong outflows and explosions. And these are the things that are propagating to megaparsec scales and then create these features in the power spectrum. Now with Illustris, this was too strong, but in IllustrisTNG, we've refined the black hole treatment. This is maybe one of the most important changes in the model. And I'm spare you the details, but with this new kinetic feedback, we achieved these successes that I discussed. And for the rest of my talk, I want to spend some brief minutes on some general remarks on resolution limitations in these calculations, because that often comes up, and then show you some brief results on magnetic fields too. So first of all, I would like to argue that and remind you that this attempt to simulate the whole universe is, of course, one that can't address much of the relevant physics that is governing, for example, galaxy evolution. I mentioned this already, right? So the cosmic large-scale structure, we're talking about scales of about 10 to the 27 centimeters or so. And, you know, the stars of growth of supermassive black holes, this is governed by, say, the accretion disk. This would be the size of the solar system or so, 10 to the 15. Even this we can't resolve in a cosmological simulation yet, let alone the stars and planets and or the thermonuclear flame fronts that are actually occurring in a supernova explosion. And this is currently and will forever be impossible to simulate in one gigantic calculation. And if you're a student, however, you might be tempted to try it nevertheless. At least that's my experience with some of my students, that they are boldly, of course, trying to do this anyhow. But you know, this is good. One should try. But I think there will always be a range of scales that cannot be addressed in a given simulation. And somehow this has acquired a bad name among some people. They then call this subgrid physics, and treat this like it's a really dirty and bad thing to do. But you know, I think it's a fact of life that you have to accept this, and one has to accept that only a subset of the valid physics can be included even in the best calculation ever, right? And then you have to ask, okay, if that's so, what does that mean? Should I therefore discard everything I learned from these simulations? And I think, you know, it depends very much on the type of question you ask. And here I show you an example to illustrate this. This is a modern simulation of a disk galaxy, where you see the interstellar medium, which is a multi-phase medium. You know, these bubbles are created by supernova explosions. And, you know, here's a thin gas disk layer from the side. So this is sort of currently what one can do, one of the best models we have at the moment. And this is the same galaxy simulated with the model from 15 years ago. Springel and Hörnquist, which uses an explicit subgrid treatment for star formation. And, you know, visually it looks very different. But you know, there's still a disk, there's still some spiral arms, but you lose all the detail of the interstellar medium. That's because this is now captured in an explicit subgrid treatment. But on large scales, this galaxy behaves just the same, right? Even the star formation rate as a function of time is basically the same. These wiggly lines are this sophisticated model. The yellow line is this very simple model. So if you only care about what is the total star formation rate of the galaxy, you know, the old model is actually not so bad. And this is sort of what often happens, that even coarse models are sometimes, for certain questions, able to give you the right answer, right? Of course, which questions you are allowed to ask is not so obvious. So now, as promised, a couple of minutes before I end on the magnetic fields. So this was something that we added to the TNG simulation because we could finally do it properly with this mesh code. So we have simulated ideal magneto-hydrodynamics as an additional equation system on top of the rest. And we put a very weak, what we call a seed field, a homogeneous magnetic field into the gas at very high redshift. A very weak field that does nothing. And you know, one doesn't really know ultimately where the fields come from. There could be primordial fields. There can also be some methods like Biermann batteries and others that create weak fields. But we started with this very weak field, and it turns out it's not very critical what type of field you put in, because we find that in these simulations inside the halos, you get a very turbulent flow, especially at the central regions. And at least in our numerical code, this gives rise to a rapid amplification of the magnetic field through a small-scale dynamo. And Kandu, of course, knows all about this, and will probably have some critical remarks about issues like resolution and so on in this turbulent cascade. But nevertheless, we find it relatively robustly, and the signatures in the velocity power spectrum and magnetic power spectrum are consistent with what you would expect from an amplification by a small-scale dynamo. And this dynamo saturates eventually once the magnetic field becomes dynamically important. And that happens only really in the densest regions of the galaxies, in the disk galaxies. And then we reach magnetic field strength. Did I show this? Yeah, here of microgauss level. This here are blue are simulated fields now that we get at the end in simulated disk galaxies, and here are typical profiles of the field strengths observed in spiral galaxies. And they have, you see, up to 10 microgauss in the center or so. And these field strengths, they are in diffuse gas in interstellar medium comparable to the thermal pressure you have there, also comparable to the cosmic ray pressure. So close to equipartition, and that's not too surprising that if you have a strong amplification process at work, like we do, that does that on timescales of several hundred mega years, then the field explosively grows, and this stops basically at a point where you reach something like equipartition, because only then the magnetic fields can really back react on the flow and sort of influence the flow field that ultimately makes the turbulent dynamo going. And we find some other areas where the magnetic fields are interesting. For example, in the so-called circumgalactic medium, this is this region of coldish gas or gas around the disk galaxy, which you see at the center and the side. And in these modern simulations, you find a lot of multi-phase structure in the circumgalactic gas. And some of these cold blobs, they are actually held up by magnetic fields in our case, because the magnetic field is sort of frozen into the gas, and once it loses its pressure support, magnetic pressure then rises to relatively strong values. What you see here, these are these magnetically strong fields in these regions. On the other hand, if you simulate the same thing without magnetic fields, we get somewhat smaller blobs, but the total mass in these blobs is roughly the same. So they are not sort of instrumental to actually make the structure, but they are playing a role in holding them up. So I'm basically out of time, so I'll spare you what I had to say about cosmic rays, just to mention that the real interest, that's ultimately also why we added the magnetic fields, is that in future calculations, we would like to go beyond this by adding non-thermal particle populations. And these are then, for example, protons that orbit, in the magnetic field, and they gyrate and are produced in strong shocks. So we have interesting plasma physics processes, very complicated to model properly, because we then have much more complicated systems of equations, even in the simplest scenarios. And the cosmic ray fluid, in a two-fluid approximation, you treat this kind of as a fluid, is then propagating and transported along the magnetic field in process like anisotropic diffusion, and you then get a coupling of these transport processes with the magnetic field direction. And that's something that is very interesting, because in idealized simulations, people find, including us, that if you do such a coupled modeling, then especially galactic winds and outflows are strongly modified. This you see in this piece of a disk simulation seen edge on. And basically this bubbling behavior, these are supernovae that go off and on, and they create kind of a turbulent quasi-stationary interstellar medium. And if you have no cosmic rays, or cosmic rays that are just locked into the local fluid, nothing, difference very small, the cosmic rays add a bit of pressure, and so we have a puffier medium. But if you have cosmic ray transport processes along the magnetic field, then you get these strong cosmic ray driven outflows that you see in this third column. And that's tantalizing for galaxy formation people, because the winds, the outflows that they are not really explained at this point. We don't get them from plain supernova thermal feedback in the way required. And so it's generally believed that other physics must play a role, and cosmic rays are one of the primary contenders here. And I spare you some of the evidence for this and jump to my almost last slide. And very much the last slide, I promise, is just making a point that I think nowadays, on a telescope of any kind, you can only run this with an instrument, powerful instrument on it, and same is basically true with a supercomputer, right? You need a powerful code to execute on the supercomputer, and this has become a challenge in its own right. And nowadays, I would argue, we're very much limited by complexity of these codes and by the fact that nobody really enjoys very much to get the bugs out of code bases of several 100,000 lines. That's what we're currently talking about. And so I encourage only also students at IUCAA to consider entering this field of numerical astrophysics, because I think the sky is the limit here, and we can still do a lot on the future computers. So my take-home points are, I try to give you a brief tour on the current state of affairs as I see it with respect to hydrodynamical simulations of galaxy formation in lambda CDM. There has been a tremendous progress actually over the last 10 years by many groups. The progress has been coming about because of better treatment of feedback physics, even though very approximate treatments, I should say, not much of this still remains to be understood, and better numerics. And with this, we make plausible galaxies on a computer. But what precisely happens to create galactic outflows, or how an AGN regulates and quenches the star formation in big galaxies, is still only poorly understood. So thanks a lot for your attention.
Thank you very much, Volker. That was an absolutely fascinating talk, and there's so much detail and so much to take in of these simulations. Let's go on to questions, because there are more than 100 people today attending. I didn't ask for questions in between the talk, but we had another couple of dozen on YouTube. The people, I'll ask people to raise their hands. There are already many up. Let's go for Rituban to begin with. Rituban, I'm unmuting you.
Hi, can you hear me?
Yes, go ahead.
Thanks.
Okay, so in the last few years, LIGO has been changing our idea of the low to intermediate range of the black hole mass function. So given that, would you say that, how you seed the black holes in your simulation, if that is made more detailed and dependent on redshift, etc., will that have a big impact on the outcome of the simulations, or do you think it's still pretty robust?
This is a very good point. The seeding is a big uncertainty. So what we do is we have a model where we seed large black holes, 10 to the 5 solar masses, in sufficiently large dark matter halos. So they are basically coming out of nowhere. Whenever a halo reaches a size of about 10 to the 10 solar masses, then it gets one of these black holes, 10 to the 5, right? So this is much larger than, of course, what we are seeing in LIGO. Also LIGO basically couldn't see these black holes yet, but we do this because from stellar mass black holes, even if you make them 100 solar masses, it's still very difficult to understand how the black holes grow so rapidly to make, say, 1 billion solar masses at redshift 6. And so we basically managed to do this, but only if we give them a head start and make them like 10 to the 5. So there are models that predict seeds of 10 to the 5 from, collapses of whole star clusters or big clouds of gas. And so currently we allude to these models. But the reason why they don't grow rapidly enough, if you assume smaller black holes, is basically because we use Bondi growth accretion, and that's also a much debated approximation, because the Bondi growth is proportional to the black hole mass squared. And there you see that if you start from a stellar mass black hole and put it into just gas and expect it to grow by Bondi accretion, you have to wait a long time, hundreds of Hubble time. So that's why we put in these big black holes. But in general, of course, we are fascinated too by LIGO, but we don't have we can't use their results directly yet. We know that if we did do smaller black holes, then we would not grow them big enough. Basically, it's one of the big open issues we have.
Okay, thank you.
Thanks. Shuchita, I'll go next. I'm unmuting you.
Okay, nice talk. So I have multiple questions, but I'll just ask one. Just a basic one. So you spoke about this Aripo. You compared Aripo with SPH, which is the moving mesh with SPH. Now, how is this moving mesh thing different from, let's say, the AMR simulations, the adaptive mesh refinement ones?
Mm-hmm. Yeah. So the both use a mesh-based discretization of hydrodynamics. The main difference is basically that the lies in the so-called advection errors. So the I mean, first of all, I would say the AMR methods are also very good. I like them, but I think the moving mesh that we have has the advantage that if you have an object, for example, a galaxy that moves through space, then in our case with the moving mesh, the moving mesh doesn't care about this bulk velocity, right? Because it's Galilean invariant. While if you have an AMR method, you basically have to place the refinements, the mesh, sort of into the path of the galaxy. You have to do this rapidly enough to not lose resolution. And you still, because the mesh is stationary, the galaxy flies with a high speed, often supersonically relative to the background mesh, and that degrades the accuracy. So you get so-called advection errors in the AMR methods that are eliminated by a repo. And also the time steps can be larger than in a repo, because when you, for example, have a cold gas, that's normally the sound speed divided, or the dimension of the cell over the sound speed sets your time step, and that's what we have in the moving mesh. But if you have a large bulk velocity that's larger than the sound speed, then this limits your time step artificially in AMR code. So they are more expensive in terms of time stepping. For example, for cold rotationally cold disks that are rotating. So in that sense, the repo method is computationally more adjusted to these flows.
So it's still a Lagrangian. So the repo is still a Lagrangian.
Yeah, it is quasi-Lagrangian, exactly, because the mesh flows with the mass, so it basically reduces mass fluxes across cells. So it's basically Lagrangian, but you don't have to. It's not exactly that. So if there's a residual mass flux, that's accounted for, and you can do the same thing as an AMR code. Also, in this mesh code, you can of course locally increase the resolution by splitting cells, and you can reduce the resolution. So this feature is retained. The adaptivity is retained in a repo as well.
Thank you very much.
Thanks, thanks, Jitendra. Let's go to Kanak. Kanak, I unmuted you.
Hello.
Yes, go ahead.
Hi, I have a question regarding dwarf galaxies. Not clear, but I'll still ask the question. Do you have any idea, regarding the number of dwarf galaxies that form in a given volume in the high redshift, like beyond redshift or redshift 2 around?
Yes, I mean, I can't give you a number now out of my head. If you ask.
My question was did you have any issues with the overproduction or underproduction of the dwarfs?
Okay, yeah. So I think the number densities of these evolve in a reasonably consistent way with what's observationally known at high redshift. Of course, the dwarfs are much harder to observe.
Yeah, because we don't have observations.
So luminosity function, the evolution of the luminosity function with redshift, the buildup also of the faint population is consistent with most of the data, I think. So we don't have a massive overproduction of the dwarfs. Also, this is also true for the satellite galaxies in, say, Milky Ways, right? So this issue whether the cold dark matter models would overpredict the number of dwarfs and satellites. That's not really there. The numbers are coming out roughly okay. That's because the strong feedback basically makes the faint end low enough and flat enough that this kind of works out in terms of number and stellar mass. But the main discussion people have here is then now about the internal structure. Basically, is the size and also the amount of dark matter in the centers, the kinematics of the dwarfs, is that correct or not? Okay. And I would say that is, I think, up in the air, in my opinion.
But in Illustris, like people have studied this.
In TNG 50 to a certain degree. I mean, we are still challenged in resolution there. So I think the dwarf, the ultra faint dwarfs and so on, that's not much studied in TNG 50 because we don't have the resolution really to be precise enough.
Thank you.
Great, thanks. Dipanjan, go ahead.
Okay, I hope you can hear me.
Yes, yes.
Yes. So Volker, very nice overview and a great talk. I will focus in on a bit more specifics of the quasar mode feedback and then come back to this problem that you stated regarding the resolution. Now, if I just allude to the earlier results that everyone has been in the community producing, that the way the quasar mode feedback works is the black hole activates and you throw out all the mass, and that's how you control the star formation. But overall, later on, as we have more resolved simulations, it's been found that it's very difficult to throw out all the mass, and especially going away from the cosmological simulations. If you look at more resolved galaxy scale simulations of a few kiloparsecs or tens of kiloparsecs, but if we have a lot of dense gas, it's very difficult to kick out all the dense gas because you need to impart a lot more momentum, which is not there in the cosmological simulation. So my question is in two parts. Firstly, how do you think one can resolve this issue of cosmological simulations throwing out all the mass, and that's how regulating star formation, and small scale simulations not finding that? Secondly, my question is, if you turn off quasar feedback and all the black hole does is a radio mode feedback, how significantly does it affect your results in respect to the mass functions, etc.?
Yeah, okay. Great question. So about the mass ejection. So I think the picture we find in the cosmological simulations is not that, also from the quasar feedback, it's not actually that much of the gas is ejected from the AGN feedback. We have this in part in the Illustris simulation where we dialed up this bubble feedback extremely strongly, but the IllustrisTNG, the black hole feedback is actually not really expelling much of the gas. You see this also that the baryon fraction in the halos is reduced at low masses, but there it's from the winds from the supernovae, and then for larger galaxies there's only a little bit dip basically in the baryonic fraction, and that's largely not from the AGN feedback. So we now think that the quasar feedback is not expelling much gas from the halo. It is still needed to stop the black hole from reaching arbitrary large masses, basically. So it's the quasar feedback in our TNG simulations basically intercepts the rapid growth of the black hole, but doesn't much expel the gas. And what the radio mode feedback is doing is it is preventing cooling of gas out of the halo. So the impact of the AGN feedback is not so much that gas is ejected out of the halo, but the impact is that cooling in the halo is stopped. So, and the AGN feedback does that by steering basically kinetic motions and turbulence and shocks in the halo that offset the cooling losses. So in a way, what we now have is that a picture where the black hole is responsible for keeping the halo gas hot without expelling it from the halo. And then the galaxy itself runs out of cold gas and stops star forming that way. So we are not expelling the star forming gas with the black hole, but we prevent that the gas forming gas, the star forming gas is replenished, right? This is a different thing. And so in that sense, our picture has changed quite a lot from these earlier generation of isolated merger experiments. There indeed, and I showed a picture, we thought that the quasar feedback would, lead to quenching by expelling all the gas there is, but that's not the picture we now have. Now it's rather a maintenance mode where the radio mode is just constantly keeping the gas hot so that no gas can cool out and make stars.
So if I just may interject here, so if I understand correctly, what you're saying is the main function of the quasar-mode feedback is not affecting directly the stellar mass budget of the galaxy, but indirectly by controlling the black hole mass evolution. Is that right?
Yes, I would phrase it that way. Yeah. So to first order, I mean, there's a little bit of impact, but you're right, and that's what I would now say our results show here. That's exactly like this. So in coming to our other question, if we would disable the quasar mode feedback, I think then we would not be able to, for example, reproduce the black hole mass scaling relationships, because that's then still set by the black hole quasar feedback. So that makes the black hole grow basically to the right size for the galaxy. And then the strong growth stops by the quasar feedback. And then in the radio mode, the black hole doesn't acquire any mass anymore, but it's now heating the halo, right? And everything stays then frozen in.
Okay, great, thanks. I know that Volker has to go eat his lunch as well, unless you have already. So, and there are many hands up. So are you happy to take more questions?
Yeah, sure, one or two, of course.
One or two more, okay. So, Shantanu, go ahead. Shantanu, next.
So just related to comparison with observations. Okay, so I'll just ask them. I'll just ask the questions. You can just give a one-word answer or elaborate on it. So I guess can the simulations reproduce the radial acceleration relation for rotationally supported galaxies and reproduce the very small scatter seen by MEGAW, although that has also been observationally challenged by other groups? But I'm just curious what simulations predict. And second question is, can the TNG simulations also produce Cormandy relation?
For the radial acceleration, I would say yes, we reproduce that. The scatter is perhaps, that would be the debate point, I think, whether the scatter is as low as some observational analysis claim. But the mean relation is, I think, well reproduced. The Cormandy relation, I'm less sure. I actually haven't seen a plot of this, but I do think that it's looking good. So that would be my guess, but I can't answer it with any certainty.
Great. So let's wind up. Let's go for one last question. I'm sorry, there are many hands up, but the next one in line is Prakash Gaikwad. Prakash, go ahead and ask your question. I've just unmuted you.
Hi, Volker. Very nice. My question is related to the ARIPO. Since we solve diffusion equation, I mean the conservation law with the Riemann solver, we inherently using some kind of numerical diffusivity. So how accurate is the shock capturing in unstructured grid, for example, in moving mesh, as compared to SPH, for example? And does it have any impact on the large scale structure shocks on the, I mean, the structure formation shocks?
Yeah, so in ARIPO, like in any other Eulerian hydrocode, typically, or finite volume method, so we or Godunov-based methods, so we use Riemann solver, and for shock capturing, that implies that you do not have to use any artificial viscosity, for example. So you can, you don't. That's what in SPH needs to be added to capture shocks, to provide the necessary dissipation, and this comes about automatically in ARIPO at basically the minimal level that is possible, in a sense, right? And so the shock capturing is very good in the sense that it's basically captured over one cell, typically a shock. And the shocks, I would say, they are basically broadened over one cell. And that's not much. You can't go much better. The quality of the hydrosolver is better judged actually with, or it's harder than when you have contact discontinuities. Because with a shock problem, you also end up getting contacts. And the contact waves, they are particularly well captured by ARIPO because there the mesh, flows along. The velocity field is continuous along the contact, and so the contact is then preserved. While in a normal mesh code, it will be washed out by the numerical diffusivity of the code. Of course, we also have numerical diffusivity in ARIPO due to the averaging after every time step that's done of the Riemann solutions, but the diffusivity is for a given number of cells lower than in a typical AMR code, I would say, right? So, but it's, as in every mesh code, you can, if you're unhappy about the level of diffusivity, what you have to do is to increase the grid resolution. And with that, you can lower it, but it's of course expensive. But compared to SPH, I would say the shock capturing is much better. And whether this is important, it depends. I mean, what many people, I think, wrongly criticize SPH for is actually that shocks are broadened. I tend to think doesn't matter to me at all. If the post-shock properties are correct, which is the case in SPH, I don't care, right? And so, it's just a bit broader, but, honestly, who cares? The post-shock properties are correct in SPH too. The problem arises that the artificial viscosity in SPH becomes active outside of shocks, and that's where the errors come in, right? Not so much in the shocks.
Thanks.
Thanks very much, Volker. I mean, I'm very sorry I can't go on to the other questions. There are many others who want to ask, but I would rather you go and have lunch in time. Applaud. It was a wonderful talk, and thank you so much, Volker, for doing this stuff.
Yes.
Thank you very much, Volker.
Thanks for all your nice questions, and all stay healthy, please.